About the delay, we are getting started. Welcome all to the second day of CoLLAs 2024. Before starting with this exciting keynote, I just wanted to remind you that we have Joseph from OpenMind here. In case you want to reach out to him, they got several openings and they are a sponsor of CoLLAs, and they have left some pamphlets in the reception desk. So in case you want to chat with them, Joseph is here. Then I wanted to remind the people that are willing to participate to the mentoring sessions that we are going to start at 1:30. Remember to be on time. And I guess that was mostly it for the logistics. Let's start with this new keynote for the day, towards a general blueprint for continual reinforcement learning by Doina Precup. And Doina splits her time between McGill University, Mila, where she holds a Canada-CIFAR AI chair, and Google DeepMind, where she is a research director. Her research interests are in the areas of reinforcement learning, reasoning under uncertainty, time series analysis, and diverse applications of machine learning in areas that have a social impact, such as healthcare. In 2022, she was elected fellow of the Royal Society of Canada in recognition of her work, among other appointments and recognition for her long career. And she's also a senior fellow of CIFAR's Learning in Machines and Brains program. So without further ado, thank you so much, Doina, for being here. And please, the stage is yours.
Thank you very much. It's really a pleasure to be here. And I also want to say my thanks to Razvan and Sarat, who are plowing along with this conference, and to the program chairs for this year. I'm very excited to be here. Beautiful city. And so actually, I wanted this talk to say a general blueprint for continual reinforcement learning, but I made less progress than I was hoping for on the research. And so it has the word towards there. But I hope that you can still find some interesting ideas and some also potential for future work, and happy to talk about that later with anybody as well. So in this talk, I want to take a particular perspective on why agents should learn continually. In general, we talk about environments being non-stationary, changing over time, and so on. But actually, the way that I like to think about this is that we don't really know much about the environment. Maybe it's changing, maybe it's not changing. But one thing that's for sure is that the agent is much, much, much smaller than the environment. Now, this might be a bit of a strange thing to say in the era of very large models. But even if you have a very large model, the world contains many other agents, right? And these agents are maybe similar in capacity to you, or maybe even bigger, right? So almost by definition, the world is going to be much, much bigger than the agent. And so if your agent is just like a little speck in there in a very vast universe, it's not going to have an infinite amount of data. It's not going to have an infinite amount of time to learn. It's not going to have sort of the capacity to compute as much as it probably wants to. And so that puts a pressure on the agent to have to continually adapt to its circumstances and to have to continually learn. And so the sort of the high level view of the agent is that there's one stream of experience. This is observations, actions, and rewards, because I'm a reinforcement learning person. If you don't like rewards, you can think of that as, some kind of loss per time step or preferences or something else that you want to optimize. And the agent is smaller than the entire environment. And specifically what I like to think about is that there's only one trajectory that the agent is going to try to take, doesn't have second chances, and it can't compute arbitrarily fast, and it can't remember everything, okay? And so that's going to mean that we can't, for example, store all the agent's experience, let's say in a replay buffer, and replay that buffer an infinite amount of time to get a perfect policy or perfect representation of the environment. We're going to have to make do with approximations. The other aspect that's kind of interesting and perhaps a little bit overlooked in current research is the need for the agent to be asynchronous compared to its environment. So the environment is doing whatever it's doing, has many agents that are not under your control. Your agent moves at its own time scale. That time scale means sort of the frequency with which it can receive perceptions and take actions. And also it can change the timescale at which it can update its representation. So oftentimes in RL papers, we think, oh, there's a Markov decision process. It's got a time that's ticking. It's ticking at a fixed timescale, but actually the agent has some power to decide when it wants to do updates. So this being said, I'm going to talk about some theoretical tools that we need for defining problems and the setup. I'm going to talk a little bit about algorithmic characteristics that might be important for us. I'll talk about a couple of algorithmic ideas and sort of end up with some conclusions and a lot of open questions, actually. So the framework that we're going to consider is sequential decision making. We have an agent at a particular time step. It receives an observation. I call the observations X. And it can take an action. The action is in the square. Now the action is denoted A. So the agent can decide what to do. That decision of what to do, we often call exploration in reinforcement learning. And as a result of the agent's action, there's some error signal that gets produced, okay, delta T. That's the sort of difference between what the agent might have expected to happen and what actually happens, okay? And I often think of that as a temporal difference error, but that could be also a supervised learning error or something else. And so there's two questions that the agent is facing. One is, how do I choose actions, right? That's the exploration problem. And the other one is, given this error signal that's been produced, how do I update my knowledge, the representation that I have, in order to make it better? Okay, and that's credit assignment. And so our goal is going to be to optimize a measure of long-term return. This is defined in various ways in the literature. There's a really nice, fairly recent paper by Kumar Marklund et al. In 2023. It's a nice big monograph on continual learning and defining it as an RL problem. That one argues that really we should be thinking about average reward. So the average of the reward per time step taken in the limit of infinite amount of time that the agent has. I don't like infinite amounts of time because I feel like agents have finite lifetimes, more or less. Okay, and so perhaps an even more interesting thing to do would be to think about a finite but random lifetime of an agent and the average reward that it gets during that. So that's going to be the goal of the agent. Now, I want to make some observations, okay? Oftentimes in reinforcement learning, we consider this picture of the whole tree of the possible trajectories that the agent might have, right? If you look at Sutton and Bartow textbook, for example, you have these pictures of trees with states and actions and next states and so on. So that's good, okay? But we're doing continual learning, and so this agent is going to have one trajectory through this tree. Okay, and so instead of thinking of this infinite tree of possibilities, we want to focus on one specific path through the tree. And this means that there needs to be some structure in the tree that allows us to learn from the previous steps that we've made to generalize into the future. Okay, so you can't have this tree be completely random. Okay, and then the interesting question is, what kind of structure do we want to think about? Okay. Now, normal reinforcement learning thinks about Markovian structure. Okay. One way to think about Markovian structure is that all of these trajectories through this tree will cluster, okay, into state. Okay. And in a finite Markov decision process, there's a finite number of states. Okay. And these, you can think of them as equivalence classes. Okay. Equivalence classes of trajectories. And if you're in some state, if you come back to that state, you're going to have, nothing else matters, right? The past, how you got here doesn't matter. And so that gives you a very strong basis for generalization. Okay? And it also allows us to build clever algorithms for doing credit assignment, right? So it's at the root of things like temporal difference learning, Monte Carlo, sort of value learning, and so on. And because we have an infinite tree of possible experiences, but we cluster it into a finite number of equivalence classes, it also makes sense to think about recurrence assumptions, right? It makes sense to think, oh, I'm going to come back to a state over and over again. And that's, again, a very powerful assumption that helps us think about exploration. And a lot of the exploration algorithms assume that you can come back to the same state. Now, there are other kinds of structure that one can have that are not Markovian. And a little bit of work has been done. Actually, this is work that's maybe more than 20 years old now. Okay. This particular line of work is looking at sort of low rank. All right. So what it says is imagine all the possible trajectories, not as a tree, but as a matrix where you have all the possible sequences of observation and actions that you could have possibly seen, all the possible futures that you could see, and you build a matrix that has conditional probabilities of the future given the past. That's called a system dynamics matrix. And we're going to consider environments in which this matrix, even though it's infinite, has finite rank. Okay. That's not a Markovian assumption. It turns out that it's a bit more general than things like partially observable Markov decision processes, but can represent POMDPs very well. So I'm curious to know what other kinds of non-Markovian structure might be interesting to explore, but certainly low rank seems like a cool idea, okay, that maybe hasn't been explored enough in the past. Okay, and it also gives you a way to generalize from the past to the future. Okay, and the particular ways that people have done this in the past is by building a small matrix from the data that you have, and because you have finite rank, you think if the small matrix is big enough, you're going to sort of capture the structure of the world, but there may be better ways to do that. Okay, so now the small agent perspective means that we're going to have this trajectory that covers only a minuscule fraction of the possible trajectories. So notions like recurrence don't really make sense anymore, okay? We still want an agent that does well along its current trajectory. So this agent is going to need to construct some kind of knowledge representation that helps us generalize. And we're going to call that representation the agent state. Okay, so, and again, there's some really nice work coming out of Ben Van Roy's group at Stanford looking at how to construct agent state and how to define it in information theoretic sense. So agent state, as opposed to state in an MDP, is an internal representation. Okay, it's not real in the world. It's something that the agent has in its head, and it represents the basis of the agent's actions. Okay, so we're going to think of policies as mapping agent state into action. Okay, and so the agent state is going to need to be learned, and it's going to need to be maintained over time based on the observations that the agent is getting, and it's going to be inherently lossy because the agent is limited in terms of its capacity, can't remember everything. Okay, and so we're going to accept that from the get-go, that we can't have a perfect agent, we can't recover an optimal representation, we just want this agent to do as well as possible. Okay, and so now we need to think a little bit about how we define the performance of the agent from a theoretical point of view. Now, this kind of idea is actually a pretty natural progression when you look at the history of reinforcement learning. The origins of reinforcement learning algorithms can be thought of as being from dynamic programming. Okay, dynamic programming means we're looking for an optimal policy in a Markov decision process, and we want this agent to do well at all the possible states in the world. Okay, if you think about the tree of possibilities, you want the agent to be optimal wherever you drop it in the tree. Now, reinforcement learning sort of took a step back and focused on states that the agent is actually encountering in its trajectories. So for example, if you play a game of Go, it doesn't matter what all the possible positions are. Many of these positions will never be reached in games. You only care about doing well in games. And that's actually very important because it allows you to sort of be less wasteful in terms of computation and do well with less data. So now we want to take this one step further and think about the agent's learning, enabling it to do well on the future of the one trajectory that it's going to encounter. Okay. And so we don't want to think about optimality as an absolute notion. We want to think about how well can this agent do given how it's gotten here. So given the data that it's seen so far, and given its computational limitation. Okay. And so sort of one example of intuitive example of this kind of thing is if you imagine, you know, I don't know how many of you have kids. I have kids, they're adults now, they cook pretty well, but at some point they were very little and they made some food and I ate it and it was pretty terrible and I was really excited because given the amount of experience that they had up to that point and given, you know, the physical limitation of something like a 5-year-old, that was quite good, okay? I wouldn't enjoy that same food from them today. So it's all relative to the agent's capability, the amount of data that it's seeing, right, and its limitations. Now, interestingly, there's been actually quite a bit of work in the last couple of years, or 3 or 4 years, looking at how we characterize the agent performance. And this is actually an area that, to me, it's quite interesting, and it's still pretty open, okay? So one way is, one thing that we need to think about is, okay, the agent has some limitations. How do we express those limitations? One way to express that is by saying the agent has a class of policies that's available to it to choose from, okay? Maybe these are policies that can be represented in some finite number of bits, okay, for example. So there's some kind of computational constraint that goes into what the agent can do. The other question is, what is the agent sort of optimal performance that we're going to compare against? So in machine learning, we use a notion that's called regret. Okay, regret means how is the performance of the current agent compared to the best possible? And typically, we have thought of the best possible as being the optimal policy, because the agent lives in a Markov decision process and there is an optimal policy. And so that seems like the normal thing that we should compare against. But in a continual learning environment, that doesn't seem adequate. Okay, first of all, we have no idea what the environment is. Maybe there is no optimal policy or overall optimal policy. And even if there were, maybe that's not attainable, right? And so what we want is to compare against something that's a good proxy or a good upper bound that maybe is achievable. And so there's these two papers, Kumar Markland et al. And Morrell et al., that try to sort of go in the direction of defining what this might be. Okay? So Kumar Markland et al. Think of this as the agent's trying to estimate something, okay? Imagine that you knew the right answer. How well could you do within your class of policies? Okay, so if you know, let's say, what's the optimal value function that can be achieved, how well can you estimate that with your class of policies? Okay, that sort of tells you what's the richness of the class of policies. And that's kind of the way that they think about the upper bound on the agent's regret. Now, this is still pretty ambitious because it assumes perfect knowledge of what you're trying to do, okay? And so an alternative to that, Morrell et al., is actually thinking in terms of, on this trajectory, in hindsight, once I do the action and I observe what happened, would I change my mind about what I just did, okay? So it's a notion of counterfactual regret based on what I see, okay, and what else I know about what other actions might have done. And so it's much more focused on a single trajectory, perhaps a little bit less ambitious, okay? Both of them have the same flavor of sort of trying to redefine what the upper bound is to be something that is more relative to the agent's capability. It's still not quite the entire sort of thing that we would like to do. Another thing that we would like to do actually is to look at data-dependent regret, in my opinion. Data-dependent regret means I also want to consider sort of what was the agent's luck so far, okay? And, you know, if the agent had an unlucky trajectory, we're not going to expect very much of it, okay? And so that's a notion that was looked at in the context of bandits, adversarial bandits, but not really very much in the rest of reinforcement learning. It would be interesting to sort of generalize this. So one thing that I'm hoping that we will see in the field in the next couple of years is actually a way to mix these ingredients into a crisp and clear and optimizable notion of regret that we can then sort of translate into algorithms. That's sort of from a theoretical point of view, perhaps what we should do. Now, what about from an algorithmic point of view? Okay, there's been actually lots of work on algorithms for continual learning and continual RL. And there's some algorithmic properties that they target. A lot of the work has been done in the stability, plasticity sort of domain, where we're trying to figure out a way of retaining information that's important, but also allowing the agent to continue to learn over time. So I'll talk a little bit about algorithms that we've developed in my group at McGill. on stability and plasticity. Another thing that we would like to have is scalability, right? So Rich Sutton had this blog post on the bitter lesson that basically says an agent's capability should scale with the amount of compute and the amount of data that it has. In other words, as the agent is progressing on its trajectory, it should be doing better and better, right? And if we make the agent bigger, it also should be doing better. And scalability is sort of one of the challenges, I would say, in RL still, because compared to supervised learning, we're actually not really able to get to take advantage as much of increasing amounts of data and compute. And so I'll talk a little bit about scalability, specifically about learning more things, okay, as we have more data and more time. And then there's a couple other things that people are not looking into as much, but I think they're very important. One is graceful degradation. Okay, so the future performance of an agent should be quite good if the future is very similar to the past, and should degrade gracefully as the future becomes more and more distinct. Okay. And then the last one is perhaps the most controversial one, self-reliance. Okay, but again, if you have kids, you're going to understand why that's very important, right? Like you want them to do things on their own. And so self-reliance basically means the agent should be able to learn from its own experience. Now, again, in the era of large models, this has been sort of moved a little bit in the sense that a lot of people are trying to take advantage of the knowledge that's sort of been distilled in these models, and that's not the agent's knowledge, right? That's our whole humanity knowledge kind of put into one network. I still think that even if you start from that, an agent should be able to incorporate its own data and its own experience in a good way. Okay, so let's talk a little bit about the stability plasticity dilemma. And I'll tell you about some work that we've done in terms of addressing this. Stability plasticity dilemma basically says we want to sort of use old information, retain it in a network to the extent that it's useful for the future, okay? And then also allow this network to have some reasonable amount of freedom to learn new things, okay? And so you might have some information that is in these red weights that we're going to transfer to current learning, and then there's going to be future learning as well. So as we learn more and more things, more and more of these weights are going to sort of be utilized, but we always want to have some amount of degrees of freedom, and yet we don't want interference. We don't want the future information to kind of pollute a good representation that we've had in the past. Now, there's been quite a bit of work on plasticity in reinforcement learning and on the loss of plasticity. There's this nice paper by Evgeny Nikishin and colleagues showing loss of plasticity and proposing a simple solution, which is just to reset some weights every so often while sort of remembering the agent's information. Even the supervised learning architectures lose plasticity. And again, there's been quite a bit of work on, for example, backdrop algorithms that try to go around this problem. A lot of the solutions that are proposed focus on this notion that we're going to reset some weights, okay? So that retains plasticity but loses stability. And so what we wanted to do is basically sort of inspired by this idea of complementary learning systems from neuroscience that Jay McClelland and others have worked on. Jay is giving the invited talk tomorrow. I don't know if he's going to talk about this, but it's a really nice sort of insight that in the brain, we have learning systems that deal with sort of immediate information, incorporating that in a very fast way. And then you have systems like the neocortex that are learning a representation that's going to be good in the long run. And that's a slow learning process. So you have some fast adaptation that's often done by remembering some things in a replay buffer. And then you have a process of distilling that into a representation that's going to be good in the long run. Okay. Now, what's the easiest way to take this and mimic it in a reinforcement learning system? Well, a lot of reinforcement learning agents rely on the value function as their main sort of knowledge representation. The value function is telling you what's the expected long-term return of the agent, okay? And you want the value function to be as high as possible. So we can think of the value function as having two components, a permanent component and a transient component. Okay, the permanent component is the one that's going to retain information over time. The transient one is going to respond to the new data, ideally as fast as possible, and then it's going to forget. And we're going to be fine with it forgetting. Okay. So it's sort of similar in flavor to these works that do some resetting of parameters, except we're not really going to reset parameters. We're just going to decay them over time, and only in the transient part. Now, I'm sure there's other ways of implementing this idea, okay, and perhaps ways that are more faithful to biology and so on. What we sort of did in this NERVS paper from last year, the simplest sort of instantiation of it that we could think of. Now, the permanent memory is going to sort of try and provide good estimates on average, regardless of the circumstances of the agent. And so what it's going to do is it's going to look at the sum of these two components and try to move towards that sum. Okay. The transient memory is going to look at the temporal difference error. Okay, so the temporal difference error is telling us how much the agent's prediction was off over one time step. And then it's going to move to correct that error. And it's not going to be able to do that perfectly, but it's going to just take a step towards correcting it. And then we're going to decay it away. And both of these components are going to get updated in parallel and incrementally, as is sort of usual in at least my side of reinforcement learning. In this paper, we used the same features for both of these functions. And so they're just like two heads on the same network. In principle, you could use a very large network and then do something like low rank approximation to represent these different parts. We haven't really done that in the paper. Again, we did something that's more sort of normal RL, deep RL-like. So I just wanted to show you a couple of results. So first results are in a prediction task. So here you have an agent that's in a little grid world. In the first side is just a discrete grid world. So we have no function approximation, just to sort of sanity check things. The agent's moving around randomly, and it's trying to predict where the rewards are going to be. And then in the second one, we have a larger grid world. There's different kinds of objects that give different amounts of reward. And what we're plotting here is prediction error. Okay, so low is good, and we're trying to see if the agent is able to predict correctly. And in order to sort of see in the first task what the agent is capable of, because this is really not a continual learning task, right? It's the agent has perfect information and whatnot. It's not really small. What we did is we moved the goal around. Okay, so every so often, every certain number of episodes, the goal is going to jump into a different corner, and then you want the agent to adapt its predictions to understand where that is. The policy stays the same. Policy is always moving randomly. And so these peaks here are when the goal moves to some other location. And we're plotting two things. The solid line is the prediction of the value for the current position of the goal. And then these dotted lines are the predictions of the error in the predictions for the values of the other goals, okay, the past ones that you have seen, okay, averaged together. And so, and we are looking at our approach, which is in blue, and then green is just usual temporal difference learning, and red is temporal difference learning with resets. In other words, we know when the task changes. Whenever the task changes, we're going to reset the weights of the TD learner, okay? And so what you can see is that the method that's where you reset the weights, as you would expect, is learning on the task, but forgets about everything else, okay, because you reset it. TD retains some knowledge of the previous tasks, okay, but as it's learning, it forgets it. All right, so as it's learning, as it's updating its estimates on the current task, these other tasks get worse. And our method is able to reduce the error on the current task and also keep reducing the errors on the other tasks. Okay, so you have some interesting sort of knowledge retention while also preserving plasticity. Okay. Now, what does this do in a control task? So for a control task, we use this Jelly Bean World environment from Tom Mitchell's group. This is also kind of a grid world, but it's very big, so you have to use function approximation. And we have here different kinds of objects, food, okay, when the agent eats these objects, it can get different rewards, and these rewards change over time. And so in particular, the instantiation that we used has some objects that always give small rewards. And then there's two classes of red and blue objects that are sometimes good and sometimes bad. Okay, they flip in between each other. And again, here we flip them sort of at particular points in time, and you see these kinds of spikes. And so here we're comparing our approach with Q-learning, which is in green. Excuse me. Q-learning is the sort of standard control algorithm, bread and butter of RL. And then red is just a random policy that's just as a sanity check. And so here we're looking at what the reward is. Okay, so this is sort of the performance measure, but we're also interested in knowing what we retain in terms of information. Okay, and so these graphs are telling you how many times the agent is actually eating particular things. Okay, so these blue these are the objects that are always a little bit good. These are the ones that are positive, and these are the ones that are negative. Okay, regardless of their identity. And what you can see is that the approach that we have, which is in blue, is sort of remembering these items, okay, doing well in terms of the reward. It's remembering the positive items. Interestingly, for the negative items, all of them actually sort of start eating more and more of that over time. Okay, except for the random, which is random and always eats the same amount of everything. And we're not entirely sure why this is happening. Okay, that's a little bit of a conundrum that we're still trying to understand. But overall, the agent is retaining knowledge, which helps it perform well over time, right? And in particular, the agent ends up sort of conservatively eating a lot of these things that give it a little bit of reward. Okay, and that's kind of an interesting approach in this particular domain. Now, one thing that I want to say, sort of as something to think about, is here we picked a task that looked at like it has some continual learning component. It's got some non-stationarity. It's not a great environment, right? And it's still very sort of artificial. And we picked it because there's not that many choices of environments right now that one can use when one wants to sort of evaluate these types of agents. So it'd be nice to have some interesting agent architectures and environments that we can all work with as a community. Okay. And now, what I want to do next is talk a little bit about representation learning as a way of improving stability, plasticity, as well as scaling. Before I do that, maybe I should see if anybody has any questions. This is going to be a little bit different than what I talked about before. Yeah. Yeah. So that's a really good point. And just to clarify, I think that looking at regret actually does allow you to talk about the learning process, because the regret formulation basically says you have, there's some optimum that you can achieve, but you're not achieving it. Now, why aren't you achieving it? Maybe it is because of the learning process, right? Because the optimum is now no longer an absolute optimum. It's defined with respect to all of the limitations that you have, right? So the capacity limitations already been taken into account. If with respect to your own representation, you're not doing well, you have high regret, that means that the learning process is broken. So I think going at it from that direction would allow us to do this. I absolutely agree with you that stability, plasticity, definitely changes, right, as you modify the learning process, also as you modify the capacity of the agent, right? Both of these things come into play. And so by no means do I want to say that it's just a matter of reduced capacity and that we have the right algorithms. I don't think we do. Yes. So you want to do both, right? You want to have in context learning, you want to sort of pour some of that knowledge back into the weights and remember it over time. I think we don't have the answer right now as to how that should be done. And again, so, what's the intuition of how it should be done? If you knew that something is information that is completely transient, okay, and you can predict that, then you don't have to remember things anymore, okay? For example, I'm in Pisa right now. I've learned a little bit about how to get around the hotel badly, but it's okay, right? I can find my way around. I'll probably discard this information because my expectation is, who knows, maybe in 10 years I'll come back here, but maybe not next year or something like that. Whereas other information about how to get around all the potholes in Montreal is just like persistently useful and has to be retained. So if you have some estimate of what would be the utility of this information in the future, you could use that. It's not clear how to obtain that and how to obtain it in a sort of data efficient way, right? And so this is where I think there's a lot of interesting ideas floating around in terms of, trying to understand what comes back and what does not, but we don't have the right answer. Just by adding, we just add them together. Again, like we did the simplest thing we could think of. Okay. So let me talk a little bit about learning representations and the stability and plasticity dilemma there, as well as the way that we can actually sort of take advantage of an increasing size of an agent and an increasing amount of data to learn more things, okay? So we want to learn about many different things. Why? Because we don't know which of them are going to be useful, okay? And one way we can think about this is through the lens of hierarchical reinforcement learning. So hierarchical reinforcement learning basically tries to construct pieces of knowledge, okay, and put them together. And these pieces of knowledge are temporally extended. So it's an example where the agent decides the timescale at which it should act, at which it should predict, and at which it should plan, okay? And so from the point of view of these kinds of trees, one way to think about it is that we're going to abstract some subtree of observations and actions into a thing, okay, a strategy, a macro action. We formalize this actually as options in reinforcement learning. These are just abstract actions that start and stop, okay? And there's going to be inside of one of these an internal policy and determination condition, okay? But mainly that's going to be constructed. When it says constructed, we can use those to act, okay? So think of this as maybe a strategy while you're playing chess, okay? You commit to it. It's a particular sequence of moves. You do it until it ends sort of naturally, or until you think that this is not going anywhere, okay? So it has an impact on exploration, and there's been quite a bit of work on exploration using the strategies, but it also has an impact on temporal credit assignment, okay? Because we can actually take a model, okay, that's a temporally extended model, and use it to propagate credit in one step, okay? So for example, if I predict that I could stretch my arm and reach the water bottle, I can then think about the value of that to me right now. And I don't have to think about all the muscle twitches and propagate credit to all of those. Okay, that's done in one step. So there's more effective credit propagation as well. The problem with these kinds of models is that they're hard to construct, okay, especially if you're going to think about all the aspects of the world. And so instead of thinking about all the aspects, which we should think, in my opinion, about partial models. Okay, what's a partial model? It takes into account some specific features, okay, only predicts those features, and does not always apply. Okay, so if, for example, right now, I would be thinking of, how to go to the airport in 2 days, well, it's irrelevant, okay, because right now I'm giving a talk. So that's just a distraction. I shouldn't really be thinking about that, right? Should be making predictions about what's going to happen today in this room during the presentation, etc. And so we want these models to apply only in specific circumstances. So for example, here we have some partial models where you have a red bit, you have an action red bit, and that converts this into a blue bit and vice versa, right? This is a partial model. The first one applies only if you have a red bit in the image, right? The second one applies only if you have a blue bit in the image, and they only make partial predictions. And that's sort of two aspects there. One is, when do models apply? The other one is, what do they actually say? Okay. When do models apply? We call that affordances. And Kimia, who's sitting over there, can tell you all about that because that was her PhD thesis. Affordances are basically a notion that came from cognitive science, from Gibson's work. And they have to do with interface between an agent and its environment. Okay. And then affordance basically says what you can do here, okay, in a particular situation. So for example, if you have a person and there's a tree, okay, that means the person can use the tree in various ways, as a shelter, to run away from animals, to have fun, etc. Okay. And so this is useful because it limits the space of possible actions that one can do. So it sort of focuses the exploration, the thinking on things that are actually doable. And it's also useful for planning purposes because we can more easily anticipate action effects. Okay. So, we don't have to think about every action in every possible circumstance and all the things that could happen. So how do we formalize this in reinforcement learning? One way to do it is to think about the agents having some intent. Maybe this intent is to achieve a particular feature value or to make a change in a particular feature value. And then an affordance relation is a relation between observations and actions that tells us when can we achieve this particular outcome that we're interested in. Okay? And so we're not going to consider all the possible actions that an agent could do. We're only going to consider the ones that are affordable. And so that restricts our choices during exploration. And also it leads to building models that are approximately causal. Okay, why approximately causal? Because we're only reasoning about actions that can achieve a particular outcome. Now, the model itself might also predict other things. Okay, so that's why it's not fully causal. But at least we know that the action achieves a particular outcome. And so in that sense, we have a causal relationship. And we can do learning and planning with this. I'm not really going to discuss the details very much, but what I want to say is that we can do this with temporally extended actions as well as with regular actions. This is one little example here. This is an old problem that was proposed by Tom Dietrich to sort of think about abstract time reasoning. Here you have a little taxi. There's a person in the taxi, and we're asking, what can the taxi do? Well, when the person is in the taxi, it can only go to places that the person wants to go to, okay? So the intent is to satisfy the person. This means that not all of the choices are available, but you have to sort of condition on what the person wants to do, okay? And so it can only go to the destinations that are allowed, and all the other places in this environment are not affordable, okay? And so we formalize this by thinking about intents, An intent is the degree to which a particular goal can be satisfied. And then we can find a metric between probability distributions of the trajectory when we have state and we're executing an option, and the probability when we have the intent, and we're only going to consider state option pairs where this intent is at least some amount satisfiable. So that allows us to sort of reduce the space of choices, okay? But it also allows us to do planning better, because we're not going to model actions in situations where they can't achieve their intent. We're not going to say anything about their consequences in those situations. And so the way that we're going to do this is by taking data, by using some function approximation to learn the option model and the affordance, right? So which states and options go together. And then we can plan using these models and see what happens. So I want to show you some results. Okay, this is the illustration in the taxi domain. And we're looking at two things here. One is the success rate. That means how often can we actually achieve the goal of dropping the person where they want using the models that have been learned. And at the top there, we're looking at the size of the affordance set. And then here we call the size just the number of states times the number of options that we have. And so this is how much we are requiring that in order to be in an affordance, option actually satisfies its goal. And here, as we are playing around with this parameter, we actually get a rate, okay, as we decrease the affordance set size, okay? Now, why do we get this sort of earlier in the training? Basically, both focusing the exploration, so the agent is not going in as many directions, and also we are getting better models, okay? The quality of the learned models is better. So the other thing that I wanted to mention, and I'll do this very briefly because I'm also running out of time, and because Safa has a poster here and you can talk to him about that, is that we can predict partially, okay? So rather than having models that don't apply everywhere, we can have models that only predict certain things. Okay? So here we're looking at a task where agent, it's got a goal state, and there's a bunch of this, okay, in the bottom half of the environment, and we just want to know basically the agent needs to build a model that helps it go to the goal, okay? And in this particular case, we can do that. We can ignore the distractors. Now, if you use something like likelihood in order to learn the model, you're going to have a lot of trouble because you do need to predict everything in the image. So what we do is we focus only on the value, okay? We do the reinforcement learning thing where the agent is only focused on optimizing its value. And so we build a value equivalent model. Value equivalent means the model only tries to help the agent plan, doesn't try to optimize the prediction for the future observation. And if we do this, we can get this sort of very fast sort of learning here with very little data. And we also are not predicting everything, okay? We're not predicting anything about these sort of objects at the bottom that are moving randomly. And so we do this in various environments. And again, you should ask Safa about that. So just to conclude, I just want to emphasize this perspective of an agent that's smaller than its environment, and that smallness puts pressure on the agent to find structure in its current trajectory online and not necessarily try to strive for optimality, okay, but just improvement over time. And that structure needs to help it do exploration and credit assignment. And I talked a little bit about these sort of temporally extended structures in both action space and model space that can help with that. Many of the ingredients that we need in order to do this kind of structured learning already exist. We have options, we have models and general value functions and affordances and partial models and so on. Again, maybe it's just a matter of actually maybe taking these things and having an AlphaGo moment or something like that, where we put it all together in some kind of integrated system. There's also a lot of open questions, okay? For example, what are good intents? What should we learn about, right? Going back to a question that was asked earlier. I don't know. I'm going to channel my DeepMind colleagues and say, maybe LLMs are going to provide clues because they're very smart. They know about everything. And we should just ask them in a particular situation, what should you do? What should you learn about? And so there's quite a bit of interesting papers actually in the last 6 months or so on that topic. I don't know. That's going to be the answer. I reserve judgment for now, but it's an interesting direction. From a theoretical point of view, we really need to formalize, I think, what continual RL should do, moving away from these kinds of recurrence Markovian stationarity assumptions to transient agents and to appropriate notions of regret. And from an empirical point of view, we should really think about the appropriate environments, metrics and baselines. So one thing that I want to say is we've all been using environments because we can get PPO to run on them, okay, or somebody else has gotten PPO to run on them, and it's easy to compare against that. It doesn't mean that it's necessarily a good continual learning environment, right? Or that the structure of the agents that have been used is actually the right structure that we should compare against. So I think, again, as a community, we should think about this a bit more, and especially about what we want these environments to capture. So one sort of hallmark of difficult RL problems over time has been reward sparsity, right? There's one goal, very hard to get to that goal. Not really clear that's interesting for continual RL, right? Because continual agents learn about many different things. There's intrinsic rewards, there's options, there's all kinds of things you could learn about. And so I think the picture that we need is more like this one here, okay, where we want to have various aspects of that are being measured, all of them, okay? Not just about performance, but also we look at the distribution generalization, right? We look at maybe transfer, right? We look at all these aspects kind of put together. So these kinds of plots might give us a better picture of what our agents should try and do. And we should try to sort of populate this picture here of the environments. Right now, we have a lot of complicated environments, but again, not entirely clear which of these we should use for continual RL. And it would be good just to get a bit more empirical experience in the community with these. So I'll stop there. Thank you very much, and happy to take more questions.
All right. Thank you, Doina, for the great talk. So we have time for just a couple of questions. Anyone? I can bring the mic. Yep.
Joseph.
So you've given maybe a few theoretical directions, and you've also shown work in small environments like Jelly Bean World. But sort of there's this thing that it's not really capturing necessarily the phenomena of interest, right? Like when you mentioned the way your child cooks or the potholes of Montreal. So what are the real world examples? What are the real phenomena that we want to capture in these smaller models that we could sort of adjust to? So maybe the potholes of Montreal is a good example, right? Because everyone's familiar with potholes and other things which change non-stationarily. Maybe cooking is. Have you thought about what's your ideal real example, even if it wouldn't be directly comparable to a simulation? Like what's the real thing that you'd like to capture?
Yeah, that's a very good question. And I think my own inclination is to say robotics, right? Because, and this is going to sound very familiar to you because you've done a lot of robotics work. I mean, you know, these examples, right? Even cooking and potholes and so on. These are, you know, things in the world. You have to mechanically get around them. You also need to reason about them, possibly at multiple scales and so on. The problem is that robotics is very hard and costs a lot of money to set up and a lot of expertise. And then you end up really wanting to get it to work and not actually focusing on the research question that you started with. And so I think, you know, at various points in time, there were these sort of aspirations of having some kind of a robotics platform that's very accessible, very easy to use. You can do things with it, and then you can focus on the research. I'm not sure where all of that has gone, but something like that would still be really nice to have.
Oh, there's another question. I already asked one question.
So I like the idea of kind of decomposing for the stability plasticity into two parts, but I think a kind of simple additive model doesn't really do all that we want to do. For example, one thing I want to learn in any new setting is which parts of my previous knowledge are no longer applicable here. So my signal that I need to do that involves kind of combining both that previous knowledge and what I'm learning now. Does your formalism incorporate that? Is there a way of squeezing that in there, or does that need a different way of approaching things?
So the permanent transient memory one does not, but I agree with you. Then there's other ways of getting to that. And so, for example, when we talk about hierarchical RL and we talk about models and affordances, right? What's affordable changes over time. That's a change that is non-additive, but we can do it, right? We can say, oh, I tried to pick up the cup. Somehow, it's really heavy today. I can't, right? So I'm going to update that model. And the update to the model is going to indirectly affect the value function because I used the model to plan, right? And so the model is going to estimate the value function differently. It's an indirect change. So that's one example in which there's non-additivity. It doesn't use the permanent transient mechanism, yet it has this kind of thing. And there's actually a lot of different ways of doing computation that have been studied, including, for example, taking value functions and doing a form of approximate policy iteration to compute the next thing. And so that sort of, by definition, excludes stuff that's no longer relevant because it's not going to be good. I think there's also really interesting stuff that's happening on the architecture side in terms of, for example, sparse models and the ability to learn pathways for propagating information within one large model where people are trying to get at this kind of information.
Yeah, and a lot of those approaches, though, get quite busy quite quickly, whereas, you're targeting quite a simple approach. Is there a kind of middle ground that maintains simplicity while providing that?
I definitely hope so. And so we've actually, Nishant has been exploring more recently ways of doing the sort of permanent transient approach that leverage, for example, shared trunks of features and LoRa and sort of sparse propagation. It's work in progress. And so I hope there's going to be a more satisfactory answer.
All right. For the sake of time, I would thank again Doina for the presentation.